Welcome to G Fun Facts Online, where we explore the bleeding edge of science and technology. Today, we are dismantling a century-old assumption that has defined physics for generations. If I asked you to picture a quantum object, you would likely imagine something infinitesimally small, like an electron spinning around a nucleus, or a lonely photon traveling through the void. For 100 years, that has been the dogma. Quantum physics is the physics of the invisible, a domain where you need complex mathematics rather than a microscope to see what is happening. But that era is ending. A revolution is quietly dismantling this scale barrier as we enter the age of giant superatoms and macroclusters. These are not merely large groups of atoms, they are engineered singularities. We are talking about thousands, sometimes billions, of atoms coerced into acting as a single, coherent quantum entity. Imagine a cloud of gas that behaves mathematically like a single giant particle, or a visible chip on a circuit board that maintains the delicate quantum state usually reserved for subatomic particles. This is the engineering of the future, and its most promising application is not just calculation, but quantum transfer, the ability to transport quantum information, energy, and entanglement across vast distances with unprecedented fidelity. In this episode, we are going to delve deep into the engineering of these macroclusters, explore how we build them, and understand why they hold the key to the future of the quantum internet. Let's start by looking at the anatomy of a giant superatom. To understand how we engineer these, you first have to grasp the principle of collective excitation. In a standard material, atoms act like a disorganized crowd. If you hit them with energy, like a laser, they all react individually and chaotically. In a giant superatom, that crowd is disciplined into a single chorus. The most ethereal example of this is the Rydberg superatom. Here, scientists trap a cloud of ordinary atoms, typically something like rubidium, and cool them to near absolute zero to stop them from jittering. Using a laser, they excite just one electron in the cloud to a high-energy state, known as a Rydberg state. When an electron enters this state, it orbits incredibly far from its nucleus, effectively inflating the atom to thousands of times its normal size. But the magic happens due to the Rydberg blockade. This inflated atom interacts so strongly with its neighbors that it prevents them from being excited. The result is that a cloud of thousands of atoms can only support one excitation at a time. The entire cloud shares this single excited state, behaving physically as one giant atom with a single, collective superelectron. The engineering challenge here is maintaining the frozen state of the gas, because if the atoms move too much, the collective state breaks. However, these are perfect quantum repeaters because the large cloud acts like a net, catching photons and storing information much more efficiently than a single atom ever could. Moving from gas to solid, we have the artificial giant or superconducting giant atoms. These are man-made chips, macroscopic electrical circuits visible to the naked eye, printed on silicon wafers. They function as artificial atoms because their energy levels are quantized, just like a natural atom. The breakthrough here is non-local coupling. In nature, an atom is small and interacts with light at a single point. In these engineered circuits, the giant atom acts like a snake, coupled to a waveguide, a transmission line for light, at multiple distant points. This allows the atom to self-interfere. It can emit a photon at point A and reabsorb it at point B, or cancel out its own emission entirely. Engineers can tune the size of the atom relative to the wavelength of the signals it processes, creating decoherence-free subspaces, where the atom holds on to quantum information without leaking it to the environment. The third pillar is the chemical superatom. This is where we create stable clusters of specific elements, like aluminum-13 or gold nanoclusters, that mimic the valence electron shell of completely different elements. For example, an aluminum-13 cluster behaves chemically like a halogen, such as chlorine. Recent advancements have moved from isolated clusters to superatomic crystals. By stacking these clusters into a lattice like bricks in a wall, scientists create materials where electrons delocalize over the entire crystal structure. Unlike the fragile Rydberg gas, these are solid-state materials that can operate at higher temperatures, offering a pathway to spin liquid states where magnetic information flows through the material like a fluid. Now, let's discuss the engineering mechanisms for quantum transfer. The Holy Grail is moving quantum information from point A to point B without losing its phase. Giant superatoms offer a unique solution through a phenomenon called superradiance. When a giant superatom releases energy, it doesn't just glow, it bursts. The collective nature of the atoms means they emit light with an intensity proportional to the square of the number of atoms. For quantum transfer, we can engineer the inverse, known as subradiance. By arranging the geometry of the superatom, we can trap the photon inside the collective state, turning the superatom into a dark-state battery that holds quantum information indefinitely until a control signal releases it. In superconducting giant atoms, transfer is achieved through waveguide quantum electrodynamics. Because the giant atom touches the waveguide at multiple points, we can engineer it to emit photons only in one direction, known as chiral emission. In a classical wire, signals bounce back and forth causing noise, but in a chiral giant atom setup, the quantum signal flows like water in a pipe, one way, smooth, and lossless. In solid-state crystals, we use magnons, which are waves of magnetic spin. Imagine a stadium wave performed by electrons. The electrons stay put, but the wave of information travels across the material. These macroclusters can be engineered with topological protection, meaning the spin waves are robust against impurities, allowing information to surf across the material intact. So how do we actually fabricate these structures? It is a mix of brute force physics and delicate chemistry. For Rydberg superatoms, engineers use optical tweezers and lattices, creating an egg carton made of light using intersecting laser beams. They drop atoms into the slots, facing the challenge of the filling factor, ensuring every slot has exactly one atom to maintain the perfect density. For superconducting giants, fabrication involves lithographic stitching. This uses standard semiconductor techniques, but with extreme precision, particularly for the Josephson junctions, which are thin, insulating barriers that give the circuit its quantum properties. A variation of a few nanometers in thickness can ruin the giant effect. For chemical superatoms, the engineering is bottom-up, utilizing colloidal self-assembly. Chemists design ligands, organic molecules acting as glue or spacers between metal clusters, to control the distance between superatoms and tune the speed at which quantum information tunnels from one cluster to the next. Finally, what are the applications beyond computation? Giant superatoms enable transformative technologies like quantum batteries. Because of the superradiance effect, a giant superatom could charge up slowly, absorbing energy photon by photon, and then release it all in a nanosecond burst of coherent energy, a quantum phase battery. They are also crucial for the quantum internet. Current networks struggle because optical fibers absorb photons, but a chain of giant superatoms could act as repeaters, catching fading photons, restoring their coherence, and firing them to the next node. There is even potential for gravity sensors. Large quantum objects are incredibly sensitive to gravity. A macrocluster in a superposition of two places would feel gravity differently on each part of its wave function, potentially leading to sensors capable of detecting underground oil deposits or magma flows by their gravitational density alone. We are witnessing a phase shift in physics, moving from the study of nature's atoms to the architecture of our own. Giant superatoms represent a victory of engineering, forcing billions of atoms to act as one to create the building blocks of the next century. Thanks for listening to G Fun Facts Online.